In a previous video on the topic of the normal distribution, we discussed how the normal distribution is just one of the many distribution types which exist within the field of statistics. And we also discussed how the normal distribution would not exist without the binomial distribution first being derived. So if the normal distribution is the grandmother of all of statistics, the binomial distribution is probably the spirit mother of statistics, or the field of statistics, applied statistics as that is. But in any case, what we have here is the binomial distribution probabilities. And as you can see, unlike the normal distribution, the binomial distribution shifts about. See, we have it here, 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 and it's going to shift about depending on what the p-value is and the n-value is in each instance. Now, p-value is not um, the p-value which you receive as far as tests are concerned with applied methodology. P-value for the binomial distribution is something a bit different, as is n. And we'll go over with the symbolic definitions of R of the various attributes within the binomial distribution in this lecture. And we'll also do a couple examples in R as well. So let's start with the definition. The binomial distribution definition. In probability theory and statistics, the binomial distribution with parameters n and p is the discrete probability distribution of the number of successes in a sequence of n independent experiments, asking a yes or no question, and each with its own Boolean valued outcome. Success with probability p or failure with probability q equals 1 minus p. So for the binomial distribution, we're going to be looking at success and failure, positive or negative, 0 or 1. All right, so everything as far as binomial distribution is concerned is either a success or a failure. Now remember that as we continue to go through these slides. So here are some of the requirements for the binomial distribution. The procedure has a fixed number of trials. The trials must be independent. Each trial must have all outcomes classified into two categories, success or failure. The probability of success remains the same in all trials, and this will become evident as we go through the examples. So here are the symbolic attributes of the binomial distribution. P is the probability of success for one trial. Q is the probability of failure for one trial. N is the fixed number of trials. X is the number of successes in N trials. And P of X is the probability of getting exactly, remember this, exactly X successes amongst the N trials. So if you're in a class and you're learning this topic, you're either going to be learning it with dice or with a flip of a coin. So either coins or dice examples. We're going to be doing dice for our examples as it pertains to these slides, and we're going to be doing our examples in R. I'll show you how to do it in R Commander in another lecture, but we're just going to be using basic R and RStudio for these examples here. So our first example, we are rolling 5 dice, okay? Now each die is a fair die, all right? It has 1, 2, 3, 4, and 5 displayed on each one of the cube faces of the die, okay? And so we're rolling 5 dice, each are fair, one after the other, and we having each face land showing a 6 side. So we want to know the probability of rolling 5 dice and all 5 land on a 6. Okay, so die 1, you throw it, 6. Die 2, you throw it, 6. Die 3, you throw it, 6. Die 4, you throw it, 6. Die 5, you throw it, 6. Or you have 5 dice and you shake them up together and drop them all at once, and it's 6, 6, 6, 6, 6. Okay? So P is going to equal 1 divided by 6 because there's a 1 out of 6 chance that a roll of 6 will occur on one die. Q is 5 divided by 6 because there's a 5 out of 6 chance that it will not, meaning that Q could be a face of 1, 2, 3, 4, or 5. Why 1, 2, 3, 4, or 5? Because they're all the die faces that are not 6. 1 is not 6, 2 is not 6, 3 is not 6, 4 is not 6, 5 is not 6. Okay? N equals 5 because we're rolling 5 times. We're either rolling the same die 5 times, or we're rolling 5 dice once, and we want 5 successes. So 5 rolls of 6 are needed. So this is notated as P x equals 5. What is the probability that all 5 rolls will show a face of 6? So this is how you would execute this code in R. dbinom x equals 5, size equals 5, prob equals 1 divided by 6. Okay? Size means 5 rolls. All right, 5 rolls. X is the number of successes. So 5 successes on 5 rolls, and the face of 6 has a 1 out of 6 chance of appearing because it only appears on each die once. Okay? So this is what this function would look like. And the underlying mechanism, which is being utilized to perform this function, is the binomial distribution. So somewhere in the back, the calculations and the integral for the binomial distribution are being applied. And then we get to not see all the doings. That's going to be handled by R. R is just going to give us our outcome. And the outcome is this value here. And I'll show you it in a moment in R. But we're just going to run this code. And this is our output in the console. And with any decimal outcome as it relates to these sorts of problems, you have to multiply it by 100 to turn the decimal into a percentage. So we multiply this value by 100, which moves the decimal point over 2 places, and then we're going to round it to 3 significant figures, and we get 0.013%. 0.013%, because this decimal point is going to come over here, 0.012, and then we round it up, so 0.013%. So what is the probability that all 5 dice that we're rolling display a 6? It's 0.013%. Okay, now let's back up a little bit here. Let's back up and talk about the requirements, and then I'll show you this in R. The procedure has a fixed number of trials. Remember, it's 5 dice, 5 dice, all right? So we're not rolling 3 dice, we're not rolling 7 dice, we're not rolling 12 dice. It's 5 dice. That's a fixed number of trials. The trials must be independent. That means that a roll of 1 die is not going to impact the roll of the other. So the dice are magnetized, they're not going to stick together in some way. So if one hits a face of one sort, the other will hit a face of another. Each roll is independent. Remember, we went over this in another lecture. These are independent outcomes, meaning that each outcome of each particular die is not going to impact the outcome of the other die. Each trial must have all outcomes classified in 2 categories, success or failure. Well, success is a face of 6. That's success. And a face of 1, 2, 3, 4, or 5, that's failure. And the probability of success remains the same in all trials, meaning that for each die roll, it's not going to change. So die 1, we don't have 2 of the dice that have shaved sides or anything like that. They're loaded. In each die, it's fair. And for each die as we roll it, the outcome is not going to impact the next roll. All right. And so we want 5 successes. Success being a face of 1, success being a face of 6, failure being a face of 1, 2, 3, 4, or 5. So this is our code. So I'm going to quick do this in R. And as a quick note, and I've mentioned this in many of my videos, all of this code here, which is taken from the slides, is in the video description. So if you don't feel like typing this all out yourself, go into the video description of this video, copy and paste this into your RStudio session, and you are good to go. You can run some tests of your own, or maybe you want to change a couple of the figures around and, for your own scenarios. And yeah, you'll be able to produce your own output. So let's go ahead and run our first example here. So here is our output right here. All right. And again, we need to multiply that value. I'm trying to, did this freeze on me? I believe that it did. However, if you multiplied this value by 100, you would get, there it is. If you multiply this value by 100, that's going to provide us with our percentage. So 0.1286%, and then you can round it to 3 significant figures, or whatever number of significant figures is appropriate for your research or appropriate for your class that you're doing your analysis within, if it is in a classroom setting, that is. And if you're finding this useful, please consider liking and subscribing. It would mean a lot. But anyway, back to the task at hand. So let's try another example. We're going to try the same experiment, same parameters, except this time we want to know the probability of rolling a 5 or a 6 on any die, and we're going to be rolling each of the 5 dice once. So in this case, a 5 or a 6 is a success, whereas a 1, 2, 3, or 4 is a failure. So let's break it down. P is 2 divided by 6 because there's a 2 out of 6 chance that a roll of 5 or 6 will occur. So 5 or 6, okay? Those are our successes, but there's 6 sides of the die. So there's 1, 2, 3, 4, 5, and 6. But we're only interested in 5 or 6. So 5 or 6 is the 2. And 1, 2, 3, 4, 5, and 6 is the 6 because it's 2 out of 6. This is the probability of failure. Those are the values 1, 2, 3, and 4 out of the full 6 sides. So there's a 4 out of 6 chance that we'll have a failure. N is 5. We're rolling 5 die, or 5 dice, as it were. And our success is we want 5 rolls of either 5 or 6. So either a 5 or 6 is successful. So we pick up 5 dice, we drop them on the floor, and we want to know the probability of each die, each of the 5 dice that we've dropped has to either have a 5 or 6 showing on the floor. So in this case, P x equals 5. What is the probability that all 5 rolls will show a face of 5 or 6? And this is what the code would look like in R. dbinom x equals 5 because we want 5 successes. Size equals 5 because there's 5 trials. All right, we're rolling 5 dice. And probability is 2 out of 6 because we either want a 5 or a 6. So that's 2 successful outcomes out of 6 potential outcomes. So this generates the result within R. So you can just run this code within R. It's in the video description. It gives you this output here. You have to multiply that by 100 to get the percentage. So we get 0.412% because we're going to round it up. 0.411, that's a 5, so we round it up. 0.412%. All right. Now let's try the probability of not rolling a 6 on one die given one trial. This is rather simple stuff. In this case, not rolling a 6 on a die. Well, you could roll a 1, you could roll a 2, you could roll a 3, you could roll a 4, you could roll a 5. Those are all the values that are not 6, but there's 6 possible outcomes. We want one outcome in our favor, that one success being either a 1, 2, 3, 4, or 5, and we're rolling one die. So what is the probability that we roll one die and we either get a 1, a 2, a 3, a 4, or a 5? That's what this code achieves here. This is our output. We multiply that by 100 and we get 83.333%. All right. Here's some other code that you could run in each instance if you wanted to take a different approach. Again, this is in the video description. Here's some other examples. This is the probability of not rolling a 6 on 4 dice, given 4 dice being separately rolled. So in this case, we want either a 1, 2, 3, 4, or 5 on 4 dice. So we roll 4 dice and we want either 1, 2, 3, 4, or 5 on each one of those dice. And the next is the probability of not rolling a 6 on 5 dice, given 5 dice being separately rolled. So finally, let's say you want to know the probability of rolling 2 or less 6s on a die face given 5 separate rolls of 5 dice. So in this case, we know that there's a 1 out of 6 chance that a roll of 6 will occur. There's a 5 out of 6 chance that the roll will not. We're rolling 5 dice, and we want 2 rolls of 6 are needed. So we want to know the probability of rolling 2 or less 6s on 5 dice. All right, so we're rolling 5 dice, and we want to know the probability that there'll either be 2 6s, 1 6, or no 6s on the dice. All right, so 5 dice come down. The probability we're looking for is either the probability of 1 6 showing, 1 die has the value of 6, 2 dice have the value of 6, or no dice have the value of 6. Because remember, it's 2 or less, which means 2, 1, or 0. Displays of 6 on our 5 dice. So this is the code that would achieve this. It's a bit different. Sum dbinomial 0, 2. All right, because again, we're interested in 0, 1, or 2. Size equals 5 because we're rolling 5 dice. And probability is 1 out of 6. So that gives us the value of 0.9645062. And if you wanted to round that, you would multiply it by 100 to get the percentage and then round it, 3 significant figures, which is 96.451%. What is the probability that 3 dice or more show the face of 6? A little bit different code here. P binom Q equals 2. Size equals 5. Probability 1 divided by 6, lower tau equals false. So again, this is the probability with 5 rolls that 3 dice or more show the face of 6. 3 dice or more. So that means 3 dice show the face of 6, 4 dice show the face of 6, or 5 dice show the face of 6. So 3 6s, 4 6s, or 5 6s on a roll of 5 dice. All right, this is how you would structure that in R. This produces the output of 0.03549,383. Multiply that by 100 and you get 3.549% if we're doing 3 significant figures. Conversely, we could also generate a result which indicates the value of the probability of 2 dice having a value of 6 given 5 dice. So in this case, we want the probability of 2 dice having the value of 6. So we're rolling 5 dice, and we want to know if 2 of those dice are going to have the value of 6. So we roll 5 dice, and we want to know the probability that 2 of the dice faces are 6 of those 5 dice that we rolled. 1 out of 6 outcome that a 6 will show up on a fair die. 2 successes, so we're looking for 2 dice with the value of 6 facing upward, and 5 dice are being rolled. So this produces a value of 0.160751, multiply it by 100 to get to the percentage, which is 16.075, 3 significant figures rounded, and that is that. So all of this code is in the video description. I'm just want to keep reminding you of that because you can change the code around to fit your needs for whatever they may be for your research or your coursework. And go ahead and play around with this. Get a bit familiar with the concept, get familiar with the R syntax, and there you go. So if you made it to the end of this video, I appreciate you sticking around. I hope that this is helpful. Please consider liking and subscribing, and have a wonderful rest of the day. All the best.